Hello everyone, welcome to my channel. This channel's for educational purposes, and we generally look at my favorite inspirations, people who have very much inspired me with their theories of everything. They're basically all-encompassing theories that purport to describe everything, to explain everything. And today is the 295th video that we have done on Dewey B. Larson's reciprocal system of theory. The reciprocal system of theory is just that, a system of theory, meaning that if you understand the system and how it works, you can apply it to any subject that you like and come up with accurate and dependable results. Easier said than done, but if you start going through my videos one at a time, you'll probably get the hang of it sooner or later. Now, Mr. Larson was an engineer that lived during the 20th century, born in 1898, died in 1990. About 1930, he started having some epiphanies about the nature of the universe that was related to his, he was working on some kind of chemistry problems, trying to make a contribution of a limited scope, and eventually recognized that he had something a lot more broad in scope, a lot more revolutionary. And so he started developing those ideas through a process of induction. And he took 25 years to work out all his ideas. I think most of his ideas a lot of it had to do with the interatomic distance between different elements and compounds. And eventually he published his two fundamental postulates, or at least declared his two fundamental postulates in the late 1950s. The first one of those postulates was the most important, and that one states basically that we don't live in a universe of matter, and we don't live in a universe of energy either. However, we live in a universe made entirely of motion. And for Larson, motion was the relationship between space and time. Space and time then are basically reciprocals of each other. They have no independent existence. They only exist together in motion. And most people rejected that out of hand. Those of whom who even heard it, how can you have a universe of motion? If you have a universe of motion, you have to basically admit that motion exists before anything that's moving. How can you have motion of nothing? People would ask. But Larson had three basic caveats to all of that. One is that space and time both have their coordinate aspects, meaning that space and time are three-dimensional, or have aspects that are three-dimensional. We can conceive very easily of three dimensions of space. This is what we're used to. But three dimensions of time went a little bit over our heads. And then Larson also said that space and time are both progressing. They both progress in a scalar manner. Scalar motion is a motion that has a magnitude but has no particular direction. It's not a concept that Larson made up. It's a concept that is on the fringes of acceptable science, very rarely discussed or used, but it's not something that Larson pulled out of his elbow. He it does have a solid scientific legacy. And a way to think of scalar motion is the clock. The clock is always getting later and later and later, but it's not moving in any particular direction. And then also a balloon with a bunch of dots on it. You blow up the balloon, all of the dots are moving away from each other, but again, in no particular direction. And this was actually observed by the Hubble telescope, which determined that all of the distant galaxies were moving away from each other. And so Larson called that clock time and clock space. So there's coordinate space and coordinate time, and there's clock space and clock time. And then there is also the discrete unit postulate, which means that space and time are both quantized. There is a minimum unit of space and a minimum unit of time. They come in chunks. If you don't have a full chunk of space, then you do not have space. You do not have any. And if you don't have two full chunks, then you only have one. And if you don't have three full chunks, then you only have two, and so on. Same with time. If you don't have a full chunk of time, even though that chunk is infinitesimally small, in the case of time, it's 1.52 times 10 to the minus 16 seconds, meaning that you can fit 6.576 quadrillion of them in 1 second. But even then, if you don't have a full unit of it, then you don't have anything. And that if you have exactly 1 unit of space in 1 unit of time, you have the speed of light, which Larson referred to as unit speed. 1/1 equals 1. And so for Larson, the speed of light was the null point, or the midpoint, or the neutral point, or the reference point, the ether, the origin of this universe. And that half of the universe is moving faster than the speed of light, while half the universe, the half that we're familiar with, is moving slower than the speed of light. And so this cuts the ground out from Einstein, who said that the speed of light is the maximum speed of the universe. If the speed of light is the midpoint or the neutral point of the universe, that creates this other half of the universe, which we know almost nothing about. But we have the potential to learn great things about this half of the universe because of the reciprocal relationship. What we know about the material sector, which is what Larson called the slower than light half of the universe, can be extrapolated to the cosmic sector, the half that's moving faster than the speed of light. Whatever is going on in the material sector, exactly that same thing is going on in the cosmic sector, except that you have to reverse the roles of space and time. In the material sector, we have relations that exhibit coordinate space, 3 dimensions of space, and clock time. The clock is always getting later and later and later. While in the cosmic sector, the sector that's moving faster than the speed of light, we exhibit, it exhibits coordinate time, 3 dimensions of time, and clock space. The clock is always getting farther and farther and farther apart. So that is an illustration of how you just need to invert the roles of space and time to go from the material to the cosmic sector. So that's a general rule there for the kind of the map of the reciprocal system universe, is that as you cross this unit speed boundary, the rules invert. And then there are two other sub-boundaries, one within the cosmic sector, one within the material sector, which are the unit time and unit space boundaries, again, coming from the discrete unit postulate. If you don't have a full unit of space, then you don't have space. You only have time. It's got to be one or the other or both. So if you don't have space, that means that you have only time. And that is what Larson refers to as the time region, the region inside where the action is occurring inside one unit of space. So this is like, our microscopic kind of things, our atomic and molecular relationships are occurring within the time region. And in the same way, in the cosmic sector, if you don't have a full unit of time, then you only have space. And so within the realm of action of one unit of time, you only have space. And Larson refers to this as the space region. And this is the realm of what Larson calls cosmic atoms and cosmic molecules. The legacy scientists would refer to these as antimatter. Okay, now Larson took those two fundamental postulates and then he developed an entire theoretical universe through a process of deduction. If this, then that, and so on. And those I covered in earlier videos from about 8 months ago, called The Outline of the Deductive Development of the Reciprocal System, where Larson takes approximately 165 steps of deduction to go from his postulates to a full-blown universe. And then he eventually wrote books on these various subjects, chemistry and physics and astronomy, and other subjects as well, including a lot of liberal arts subjects. Now, then Larson developed somewhat of a following, not a big following, very small, but dedicated. And they started a journal that was called Reciprocity that stuck around for 20 years or more. And after Larson died, there were a few people that kind of tried to fill the void and continue to put out content and to refine his ideas, revise some of the sticking points, which Larson admitted existed. He believed that the theory itself was correct, but whether he applied the theory correctly in every case was a different matter, and he was subject to error. And a few of Larson's followers have, I think, discovered a few of the errors that Larson has made. In particular, Dr. Bruce Perret, the late Dr. Bruce Perret, who worked along with Dr. KVK Nehru to come up with what they called RS2, the Reciprocal System 2, the re-evaluation of the reciprocal system. And we're going to look at, we are looking at an article written by Dr. Nehru that is called, what is it called? The Space-Time Universe is what I believe it's called. Let me make sure that's correct. Yes, the Space-Time Universe. And he put this out in the late 1970s. It is not published by Reciprocity until much later, but we read through the first. This is a summary to a certain extent of not only the reciprocal system, but kind of like the terrain that it encountered once it was out in the open. And the first section that we went through yesterday kind of covered the mainstream legacy scientists and some of the weaknesses of their theories that Larson's theory addresses. And so we're about to read part 2 of this theory here today. Part 2 relativity, gravitation, and the macrocosmos. Now, for some reason, I feel like I've read this the beginning here. Yeah. Let me see here. I'm sorry. We did read. Okay. Yeah. This part 2. Okay. We have seen in the previous article that the present state of the theory in physical sciences requires a re-examination of the validity of the most fundamental of the scientific concepts. This is the task to which Dewey Larson, an engineer scientist from Oregon, USA, has addressed himself to. To be sure, this is an enterprise of immense arduousness, since it requires an open mind, which means the ability of the mind to step out of the inveterate patterns of thinking, to do this without transgressing rationality. His researches reveal to us a most unexpectedly simple theory that encompasses all physical phenomena of the universe from atomic to galactic magnitudes. He shows in his work how his predictions completely agree with the present observational knowledge in all different domains, answers the long-standing scientific puzzles, and take us into regions as yet unexplored by current science. His theory explains the origin of gravity and the nature of radiation, the galactic recession, the atomic structure, cohesion, electricity, stellar evolution, radioactivity, and cosmic rays, among other things. What is more striking is an extraordinary propinquity of the theory to the viewpoints of occultism. A brief, and again, occultism does not mean evil. It does not mean, satanic. It means hidden. Occultism means hidden. Hidden usually in plain sight, right in front of your face. Something that is occult is something that is not well known. And there's a history of occultism, of people that have written about things that are hidden. A lot of times they're hidden within, our layers of consciousness. A brief survey of the development of his reciprocal system of theory, as Larson calls it, is presented below, with a view to appraise its comprehensive nature and to show how it throws fresh light on occult chemistry. And occult chemistry is capitalized there. That refers to, specifically to a book called Occult Chemistry that was written by Annie Besant and I think Leadbeater. And they actually went through a mystical process of shrinking themselves down to the size of atoms and then clairvoyantly looking at atoms from, at that scale, shrinking themselves down to the scale of atoms so that they could see what atoms looked like. And, whether you believe what they did or not, they were able to map out all of the atoms and show their qualities. And this is a book that's called Occult Chemistry. I think it came out in the late 1890s sometime, although I'm not sure of that. Maybe Nehru will let us know. This section is called Space and Time. The author points out that space and time are the most fundamental concepts, the correct understanding of whose nature and characteristics should precede any theoretical development. Basing solely on what is revealed in direct observation and not on any interpretation, the following can be said of them as being true in the local environment. This is coming right from Larson's first fundamental postulate. Space is three-dimensional, homogeneous, and isotropic. Time progresses uniformly and perhaps only locally, unidirectionally. Or I would say time progresses uniformly and unidirectionally. And the scalar relation between space and time is reciprocal. That is, speed equals space divided by time. And this relation constitutes motion. Larson takes pains to clarify the meaning of dimension and that time has no dimension in space. Time enters into the mathematics of the physical processes as a scalar quantity. From this, the physicists have jumped to the conclusion that time is one-dimensional. The point that the physicists have overlooked is that direction in the context of physical processes, which are represented by vectorial equations in present-day physics, always means direction in space. Then he reminds us that no matter how many dimensions it may have, time has no direction in space. There is nothing in the role which time plays in the equations of motion to indicate specifically that time has more than one dimension. But a careful consideration does not show that the present-day assumption that we know time to be one-dimensional is completely unfounded. Then he makes the important assumption that the relation which we find in the region accessible to observation also holds good in the inaccessible region of the universe. The first and most important conclusion that can be drawn now from the extrapolated relation is that inasmuch as this specifies the existence of a general reciprocal relation between space and time, there must be complete scalar symmetry between these two entities. Hence, he calls his theory the reciprocal system, basing on further observational trends on the existence of discrete quanta. Two postulates are arrived at, from which and which alone the entire theory is developed. The first fundamental postulate: the physical universe is composed entirely of one component, motion, existing in three dimensions, in discrete units, and with two reciprocal aspects, space and time. And then the second fundamental postulate: the physical universe conforms to the relations of ordinary commutative mathematics. Its primary magnitudes are absolute, and its geometry is Euclidean. And as I mentioned, the second fundamental postulate is subject to some dispute, including from Dr. Perret and presumably also from Dr. Nehru, about, in particular, the geometry of the universe. But we will get into that later. The validity of these postulates is established by comparing the logical inferences drawn from them with actual facts observed in nature. The domain of the predictions ranges from the heart of the atom to the farthest reaches of the universe, and not one single case of discrepancy with facts seems to be present, while there is much light thrown on phenomena that have so far not yielded to present-day science. In view of the symmetry between space and time, it turns out that any property of one of these is also the property of the other. More specifically, this leads us to the conclusions that time is also three-dimensional and that space, too, progresses like time. It must again be pointed out that the dimensions of time are properties of time and do not have anything space-like. Though the three-dimensionality of time may look strange, nothing in our experience contravenes this possibility, even though it may not point out to this possibility. In fact, Leadbeater speaks of three-dimensional time in his book, The Monad. More bizarre may look the concept of progression of space, similar to the observed progression of time. But the fact is that we have actual observational evidence of the progression of space in the recession of the distant galaxies. Further, when we analyze the motion of the distant galaxies, this turns out to be scalar. The motion actually has no specific direction. It is simply a scalar motion outward from all other galaxies. It is important to clearly understand the nature of the scalar motion. It is either outward from all other locations or inward toward all other locations. A scalar motion has no inherent direction, unlike the motions of our everyday experience. As an example, consider an expanding balloon. The different points on the surface of such a balloon move outward from each other. The movement of any particular point, as far as the balloon itself is concerned, has no inherent direction. Its motion is scalar, simply away from all other points. The direction is acquired only if the balloon is related to a stationary reference frame, like the room in which the balloon is situated. In the light of the above, we must revise our view of the running of time as a unidirectional flow. It is rather a scalar progression It is rather a scalar progression. That is, each location in time is continually moving outward, away from all other locations in time. Now, if space is also progressing scalarly, that is, expanding outward incessantly, why we are not aware of it just as we are cognizant of the progression of time? Or I think he means, why are we not aware of it just as we are cognizant of the progression of time? The reason is that in our environment, this outward progression of space is counterbalanced by a scalar inward movement or inward motion engendered by matter, and we seem to see a stationary space. So the reason why we do not detect the progression of space is that in our environment, this outward progression of space is counterbalanced by a scalar inward motion, which he eventually refers to as gravitation. A scalar inward motion engendered by matter, and we seem to see a stationary space. Okay, I think we're going to stop right there because he goes on in this section for a while. We're going to stop right there and take over tomorrow with the rest, well, not the rest of this paper, but the next installment of the paper. This was the second installment. So if you wanted to go from the top, you can go back and listen to yesterday's video as well. But in the meantime, hope you have a great day, and thanks for tuning in.